AI is about building machines that exhibit various aspects of intelligence. For example, using massive computing power, Deep Blue beat the world champion Kasparov at chess in 1997.
Queen c2 to e2. Checkmate.
However, even the most advanced robots available today have trouble making sense of the complex, unstructured world we live in, and they often fail to choose appropriate actions. Children learn to manipulate objects through trial and error, and machine learning algorithms are empowering robots to do the same. Still, it's very difficult for a robot to realize that there are pieces on the table which represent the chess game, and that they must be manipulated in a certain way. In order to learn abstract concepts like the pieces on the board represent a chess game, the robots must be able to explore and learn with much greater autonomy. To recognize interesting things to learn, there must be an intrinsic motivation that comes from within the machine. This intrinsic motivation can also be viewed as artificial curiosity.
The I'm Clever project is about developing intrinsically motivated, cumulative learning versatile robots. It is a 4-year research project that started in 2009, is funded by the European Union, and involves 8 research institutes from 5 different countries. The focus of I'm Clever is on learning through intrinsic motivation on all levels of cognition, from sensory data processing to action synthesis.
Reinforcement learning is a promising approach to building intelligent systems. However, it's unclear how well they scale up to modern complex robots. A reinforcement learner is usually rewarded for achieving some external goals. For example, building a tower of blocks. Ideally, we should not specify the external goals directly. We should let the system choose its own goals and allow the behaviors to emerge. The demonstration shows that a curious reinforcement learner can produce emergent behavior. However, it is just a simple manipulation demonstration. The control and the vision subroutines were carefully engineered. The state space is small, and the learning problem is therefore manageable. In the future, curiosity-driven reinforcement learning needs to be scaled up to more complex robots, like the humanoids, which have much larger state action spaces.
The iCub humanoid robot is an interesting research platform because of its versatility. Like us, it's physically capable of reaching, grasping, and manipulating objects in many different ways. We hope to show that our learning algorithms can choose actions intelligently in many different circumstances. Controlling the iCub in an intelligent way is very difficult. Consider that skills we perform without even thinking actually take us many years to learn. For example, picking up a glass from a cluttered table and raising it to our lips. To build up simple object manipulation skills, the iCub must solve many subtasks at the same time. It doesn't start with the notion of an object. It only has a massive stream of sensory data. It knows what the position of its motors are in degrees. But it doesn't know where its hands are in the room, or that it even has hands. Because the synthesis of intelligent manipulation behaviors is such a complex problem, we have developed a learning architecture to help organize our efforts. This architecture, which we call Clever K, allows us to try out solutions to sub-problems individually, and it enforces modularity such that we can easily reuse the most effective solutions. Modules are organized in a hierarchical structure. At the bottom are simple modules that learn things like this group of pixels represents an object, or close the hand. Higher level modules learn more abstract things like my hand is near the cup, or put the cup in the box.
We have realized the Clever K architecture as our modular behavioral environment, or MOBI, which decomposes the complex learning problem into manageable chunks. Behaviors are implemented as a distributed system of loosely coupled modules which communicate via Ethernet. MOBI employs a hub-and-spokes architecture which minimizes dependencies between the different modules and therefore maximizes the reusability. MOBI's hub is based on a geometric model of the robot and its surroundings. Coupled to the geometric model is a port filter whose job it is to regulate the contributions from the other behavioral modules running elsewhere on the network. These behavioral modules fall into one of the following three categories. Sensory modules discover and compress the state of the robot and of its surroundings. Agent modules draw on the world state and plan deliberate actions to either explore the world or to exploit knowledge previously gained. Reactive control modules implement reflexive behaviors, such as closing the hand when an object is detected near the palm. The geometric model within MOBI allows us to define a very powerful and general state machine. For example, we can define all kinds of useful states, like the robot's pose is self-colliding or not, the hand is interacting with a target object or an obstacle, and we can use these states to control behavioral learning. In order to compute states like these, we rely on sensory modules. Learned computer vision modules process raw camera feeds and can identify and locate objects of interest in the robot's environment. In addition to these concrete geometric states, MOBI's hub can relay supplementary state information from autoencoders, slow feature analysis, or any other kind of learning machine. In this way, we can represent abstract concepts like an object is standing or has been toppled, or an attempted grasp has succeeded or failed.
For a robot to see, it must create a usable representation of its environment from visual input data. On the iCub, that means to process the video streams from the stereo cameras to do object identification and localization in the robot's workspace. As the iCub reaches for an object, it usually has to move its torso. Therefore, it also moves its head, and to keep the gaze fixed on an object, it also needs to move its eyes. All this motion is problematic for standard computer vision algorithms, which are based on protected geometry and need to be carefully calibrated. Another problem is the sheer amount of computation that has to be done. The computer in the iCub's head just won't do the job. Therefore, the task has to be distributed over the network, which introduces problems like latency and synchronization. IDSIA Vision is our framework for developing distributed, reusable computer vision modules for tasks like object detection and localization on the iCub humanoid. Currently, we're interested in object manipulation behaviors. Therefore, we have focused on two modules to implement sight on the iCub for this specific purpose. The detector detects an object within the images being streamed from the robot. The locator locates the object in 3D space. This is done continuously and in real time. The results are then used to do gaze controlling and reach planning. Our best detectors are based on Cartesian Genetic Programming, or CGP. Using the Open Computer Vision Library, CGP learns to apply a series of filters to separate the object of interest from everything else in the image. The learning only requires a handful of examples of correctly segmented images, and the resulting filters are incredibly robust to camera motion and the change of lighting conditions.
Processing iCub vision data can be quite a challenge. Much of it is because of its massive size. In fact, iCub can produce up to 10 million pixel intensities per second. Slow feature analysis compresses complex sensory data by focusing on parts that change. It builds a compact representation based on a few relevant features. The compression algorithm gives priority to the components of the data that change slowly, the first feature to emerge being the slowest, and the second a bit more faster, and so on. This makes it robust to noise, as noise typically changes at a faster timescale. Slow features can represent abstract states that are hard to describe. For example, our iCub has learned to represent the state of the cup as either standing or toppled. Importantly, this is done on using raw pixel data with no pre-processing.
Our behavioral decomposition differentiates between deliberate and reactive behavior. These are handled by the agent and the controller, respectively. The agent plans actions, and the resulting motor commands are sent to the MOBI hub and eventually executed by the robot. Currently, the agent is based on a roadmap, a graph embedded in the robot's 41-dimensional configuration space. The vertices of this graph represent full-body robot poses, and its edges represent motions that take the robot from one pose to the next. We've implemented several agent modules which learn to plan motions through this graph in different ways. The defining feature of the agent controller system is that it can recover from planner failure. When the agent executes an infeasible action, a reflex is invoked, and the robot returns to a previous known state. The active edge is then penalized or removed from the graph completely, and the agent must replan the action. Therefore, we don't have to verify the feasibility of all of the graph edges preemptively, which is quite practical if the graph is very large or if the robot's environment changes. Roadmap graphs can be constructed autonomously online as the robot explores. However, because the iCub state space is so large, it can take a very long time before this process goes anywhere. A practical alternative to building the graphs from experience using the real robot is to search for sets of interesting poses using Moby's geometric model directly. By leaving the hardware out of the loop, we're able to search for poses much faster than real time.
The iCub state space is extremely large, and sampling it completely is infeasible, even at low resolution. We therefore focus on finding sample sets that are task relevant. The kinematic model allows us to sample much faster than real time without actually moving the robot. The sampling sequence is determined by a black box optimization algorithm called Natural Evolution Strategies, or NES. The optimization is controlled according to the iCub's geometry. For example, NES can deliver us a set of pre-grass poses for objects on a table.
Using modular reinforcement learning within the Moby framework, the iCub can autonomously learn behaviors that lead to different slow feature values. These behaviors or skills can be combined into composite behaviors. For example, skills like reach, pick up, move around, and place can be combined into put the can in the box or sort cans and tea boxes.
The first goal of this project is to make robots more autonomous, more adaptive, and therefore more versatile. Our second purpose is to create a meaningful dialogue between AI researchers, roboticists, and scientists that study learning in biological systems. Through this dialogue, we can all learn from one another. And in that sense, we have